WABYA here. A very quick video. This time we're going to be evaluating the common mode rejection of some various RF chokes that I'm going to make up and then evaluate. The setup's going to be really easy. We're going to be sweeping basically from 9 kilohertz up to 2 megahertz. I've got tracking generator output coming over. We've got the return coming over. We've normalized this signal. So that's the top trace along the top there. 5 dB per division. So we should be able to see down to 50 dB, minus 50 dB. The question I had going through my head was, I have a pretty good idea what happens to a ferrite toroid like this. This is type 75 material. I know what happens as I increase the number of turns. Because I'm going to ultimately be using a coax like RG316, I know that using this wire instead of the RG316, I'm going to get a slight difference in the results, but it should be pretty close. I know the interwinding capacitance is going to have some effect, and number of turns that I can put on the toroid are going to be different when I switch over to a slightly fatter conductor, outer conductor like the coax. But this should give me a pretty rough idea. What I'm going to do, I'm going to keep the number of turns fixed at 15 turns. And what I'm going to do, we're going to get a baseline of what one toroid choke, what the common mode rejection should be close to. And then what I'm going to do is I'm going to start stacking additional ferrite cores together and then winding the same 15 turns around 2 cores, and then we'll be evaluating it. We'll see how the common mode rejection changes. And then, because we can, we're going to stack 3 of them together and do the same measurement, and then we're going to stack 4 of them together. So that should be fairly interesting to see what 4 of them in the same 15 turns, what that does. As a final test, what I'm going to do is I'm going to take these remaining 4 chokes, toroids, and we'll stack them up like this. And we'll put them like that. And what we're going to do is we're going to run 15 turns around both of them like that. So in effect, we'll be having 8 ferrite toroids and 15 turns going through them. And we'll see what the common mode rejection looks like. So I thought it'd be kind of a fun experiment. I've made lots of tests where I just varied the number of turns through a single toroid, but I always wondered what would happen as I started increasing the actual number of toroids. So anyway, the setup is running. We've got a normalized trace up here. I'm going to go ahead and piecemeal a bunch of videos together. I'm going to go ahead and remove this bottom wire. We're going to substitute this RF choke in here, and we should see the common mode rejection increase as we increase in frequency, and the common mode rejection should get less and less and less as we go lower and lower in frequency. So Let's see what happens. All right, here's the results of the single 15 turn ferrite core. Pretty nice looking response. There's a fair amount of rejection, out to about 2 meg. Looks like there's about 35 dB. What I've done is set up 4 markers here, starting at 50 kilohertz, and then 100 kilohertz, 150, and then 200 kilohertz. But I'll kind of hold it here for a second so you can see what the graph looks like. And real quick, we'll just generate a table so that you can see. There's the actual numbers. So 50 kilohertz looks like a little over 12 dB, 100 kilohertz about 20 dB, 150 was about 24 dB, and 200 kilohertz is about 27 dB of rejection. So let's go ahead and double the number of cores and we'll see how it responds. It might be kind of fun. I'll see if I can save this trace here. I think I'll do that, and we'll keep the same markers. All right, pretty interesting. We've got 2 toroids now. Same 15 turns using the same wire. And we can see we've got more rejection, especially at the lower frequencies. It looks like I'm going to be running out of range at the low end, so I may have to change my scale when we go to additional toroid cores. Rather than 5 dB per, I may have to change this to 10 dB per. But let's go ahead and generate the marker table. You can see the numbers. So yeah, nice improvement. Almost 19 dB at 50 kilohertz, 26 at 100, 30 at 150, and 33 at 200. Well, let's go ahead and wind three cores together. And like I said, I'm gonna have to change the scale here. I'll try to keep these curves up, but we may lose them, so cross your fingers. All right, so we made up the next choke. I'm gonna cheat. I used 4 toroids instead of 3 because it's a lot of work. I'm being lazy. I've set up a third trace, the blue one, that is with 4 toroids stacked. And we'll go ahead and let you look at the low end there. Again, this is going from 9 kilohertz to 2 megahertz. So let's go ahead and generate a table. And here's the numbers that we've got. Let me make sure that can focus. So 25, 32, 36, not quite 40. What's interesting is you can see as the frequency is getting higher, the plots, the graphs are starting to merge, and that has to do with the inner winding capacitance. I'll go ahead and get you the part number also for these type 75 ferrite cores. I'll give you the exact part number on the next go around. So now the next step will be to use 4 next to 4, and we'll run 15 turns around it, and we'll see what happens. I suspect the high end may even get a little bit worse, but probably will get a little bit better here at the low end. So we'll see if it's worth it to go from 4 to 8. All right, so now we've got a total of 8 cores, and we've got 15 turns. We're doing the concentrating on the bottommost trace, and as we suspected, down at the higher frequencies, the curves are starting to merge. Where we do notice the most difference is at the lower frequencies. Before I forget, let me give you the part number. So there they are. These are ferrite cores. They're 26, 75, 82, 1502 cores. So let's go ahead and generate the table, and we'll see what the numbers are. So it looks like at 50K, we're getting about 30 dB, 100K, 37, 150K, not quite 42, and at 200K, about 45 or so. So is it worth it to go from 4 cores to 8? I don't think so, in my opinion. What I'm probably going to do is use 4 cores at the antenna, and then 4 cores at the receiver. And of course we'll be using RG316 rather than this bare wire, well, not bare wire. This is multi-strand, multi-conductor stranded wire, silver coated Teflon. So that's what we found. Looks like, as we suspected, at the lower frequencies where we're going to see the most help. And since I'm primarily interested in VLF anyway, I'm interested in frequencies from about 250 kilohertz down. I think that'll be a good compromise to stick with 4 cores at the antenna. I just can't see justifying using 8 at the antenna and then an additional 8 at the receiver. So I hope you found this helpful. If you have any questions, feel free to leave a comment. 73 WABYA. At the last minute, I had a change of heart, and I decided, after looking at the data, that I wanted to have 8 toroid cores at the antenna rather than the 4. And that is because the difference going from 4 to 8 was pretty significant. It was close to 5 dB more improvement, especially at the very, very low frequencies where my primary interest is. So what I've done is set up the instrument exactly the way it was before, and you can see the data here. One big difference is I'm now using the actual coax. Coax is very similar to RG316, It's got a Teflon jacket over it, but still silver coated braid. Very high density braid. And I've added a few extra turns on there. There's about 18 turns on here. So I know it's not apples to apples. Before I was using 15 turns. But what's very interesting is what a sharp dip we have. And for me, because I'm interested in VLF below about 250 kilohertz, couldn't ask for anything better. This is right at 250 kilohertz. You can see it's hitting 60 decibels common mode rejection, which is I think pretty outstanding. We can go ahead and generate the table. You can see the numbers there. Pretty impressive. I really like using the 8 toroid cores. So that's what the numbers look like. What I also did was I generated and you'll have to forgive my penmanship here. It's very, very poor. Very interesting results. You'll notice going from 1 turn to 2 turns, we doubled the number of turns. We see a 6 decibel improvement in the common mode rejection, and that's right up to 200 kilohertz. If we go from 2 to 4, again, we've doubled the number of toroids. We see, again, very close to 6 decibels all the way down. The only place it starts falling apart is when we go to from 4 to 8, we only see about a 5 decibel improvement, but that's still pretty significant, especially for me at the very, very low frequencies. You know, I'd rather have an extra 5 dB, especially down at 50 kilohertz. And then I wanted to know the difference between, I think this is very valuable information. These were tested using wire, stranded wire, and this was used, data was collected using coax. So I was curious to see if there's a difference when using a setup like this, if there was going to be differences using wire or using coax. And I think had I stuck with 15 turns here for the coax, the numbers would be probably very close to identical. So at least for the low frequencies, well, here we see some discrepancy up at the higher frequencies, but that's because of this very, very sharp dip that we see. But I think for the most part, for very, very low frequencies, for VLF work, using wire or coax below 100, 150 kilohertz, you're not going to see a very significant difference between wire and coax. So if you want to do some experimenting, feel free to use coax or wire, and then once you've got the results that you like, you can switch over to coax. For example, I was not going to waste coax to run these evaluations, so that's why I used wire, because I've got thousands of feet of it right there. I don't have that much coax available. I wanted to save that for the very end. So there's the results, and I'm going to try something here. I don't know if it's going to work. I'm just kind of curious if I can zoom in on this. I may have to renormalize the trace, but I want to see what happens here if we change the stop frequency. I don't know if it's going to let me with all this data here. You know, we'll change it to 1 megahertz. No, it's not letting me. I'm going to go ahead and, just for the heck of it, because I'm very curious for myself, what the common mode rejection is down to say 10 kilohertz up to say 1 megahertz is. And I also may run it up to say 15 or 20 megahertz. Now, for some of you, you may be saying, well, okay, up at 2 megahertz, the common mode rejection was about 30 decibels on a choke like this. And you may be saying, you know, that may not be enough. And as we go higher in frequency, it'll slightly get worse, but I suspect not too much worse. Very, very easy solution to that is, don't forget, you can always add a different core material after this choke. Say, rather than a type 75 core, you can use a type 31 core. So grab, say, a pair of type 31 cores and wind common mode choke, and you can put it right in series with this choke, and that will provide more common mode rejection at the higher frequencies. So if you need something more broadband, don't hesitate to add a different choke after this one in series. And it's very, very possible I could have stacked directly on top of these type 31 core, but my enclosure is not big enough to, as you can see, this is a pretty good size, but this is going to fit inside the enclosure that I have in mind, and we'll be putting it out at the antenna, the receive antenna. So I'm going to go ahead and rerun this. I'm going to renormalize it, and this time I'm going to run it up to from 10 kilohertz up to say 1 megahertz or so, or maybe even 500 kilohertz, so that we can get a very detailed look at what the rejection numbers are there. I generated a new plot here. This time we're going from roughly 10 kilohertz up to 500 kilohertz. So we're looking at approximately 50 kilohertz per division. There's 100, 200, 300, 400, and 500. This gives us a better idea of what to expect, especially at these low frequencies where I'm primarily interested in. I really like the results. I did change this number 1 point. I made this at 10 kilohertz. I was just curious. Let me generate a table. So there we can see. Isn't that amazing? Look at the drop at 10 kilohertz. Only 8 dB. But at 50 kilohertz, it picked right back up. All right, well, there's the darn phone. All right. This will be the last video clip. What I've done is I've made the spectrum analyzer sweep from 10 kilohertz to 30 megahertz. I was just curious to see how horrible the common mode rejection would be at the higher frequencies, and it's worse than I thought. So this is definitely going to serve my purpose for VLF work, but this is not something that you would want to use for HF by all means. So we can see at the low frequencies we've got plenty of common mode rejection. I've made the cursor here. We can see you know, here we've got 30 dB down at 2.5 megahertz. We're climbing up. There's 3, there's 4 megahertz. Well, anyway, looks like the break point is about 8 megahertz. We get about 20 dB. So there you go.